Okay, good morning. This is Elizabeth Janicek at CERL. I wanted to start out this morning. Thank you all for agreeing to meet a week late than all the rest of the briefers to hear our outbrief of this 2011 project. I wanted to start on this end by acknowledging and introducing the people around the table. First, I want to introduce Martin Page, who was essentially was a co-PI in the project. He's an environmental engineer here at CERL. Hello.
Yeah, that's what
and then Andy Herr.
This is
Andy Herr is a civil engineer here at CERL. Has been assisting Martin with the gray water work and a lot of other water projects here at CERL.
Hello.
And then Noah Garfinkel, another civil engineer who's working on all things water as well here at CERL.
Hello.
And so we're going to take turns this morning. We're going to step in as need be and as expertise indicates to address all the topics this morning. Okay, so we're going to go ahead. Advancing slides, working okay?
Still on the first one, Elizabeth.
Okay.
Yeah.
How do I do that?
Yeah.
I did send out the slides within the invitation, so you could just say what slide you're on.
Sure. Okay, go to slide 2, please. I've got it selected, but it's not. Okay, there we go. Okay, this is our total slide. Hello? So this is our project overview slide. Basically, our technology was a combination of water conservation and gray water reuse in order to use the right quality of water for the right end use within buildings. And the main difference of this project with others is that we were using these technologies in existing buildings. That is, trying to retrofit the majority of building stock that are already exist in Department of Defense. Right here you see a summation of our results, and we're going to go through with detailed explanation of how we came about with this. We had several hurdles in the contracting process. It was quite lengthy and grew to be expensive. Also, there were some legal requirements we had to deal with. And we're going to talk at length about some of the metering challenges. We think the technology transfer outlook is good for some applications of gray water, not so much for where it was used in this project. And it lists our 2 demonstration sites on the bottom of the slide. Okay, next slide, please. So our entire project team, it was a purple project, a DoD project. We have a Navy partner, Gary Anguano, who's online, and he accompanied us on some site visits. We also had an Air Force partner involved in this. And then we had our 2 sites. Now initially we started out with Fort Irwin, California as one of our demonstration sites, but what happened there was we had a change of command and they were no longer interested in hosting. So we ended up demonstrating at our local site, which is the CERL site, and where you see the University of Illinois listed, we happen to be tenants of the University of Illinois here at CERL. And so we worked with them. They are the owners and operators of the building. And then our second site was out at the Marine Corps Recruit Depot in San Diego. And Richard Hatcher was instrumental in providing data and support for our many trips out there to San Diego. And then on the right, I wanted to acknowledge all of the other people that contributed to the project. They didn't start out of the project at the beginning, but they provided a lot of support. They stepped in where we needed it as the project went on. Next slide, please. Background. We should be background. Okay, technology description. So this is an overview of the technologies that we included in the project. It shows the plumbing retrofit technologies that we used, and it also lists the gray water technologies. There were 2 types of gray water technologies we were interested in. One was a building scale, a large scale, and that was targeted towards a gang shower, gang latrine that we see in a lot of our training barracks. And then the second level of gray water was what we call the tap to toilet. And that is collecting sink water and using it to flush toilets locally within a room within a building. Okay, next slide, please. So our technical objectives, again, were to retrofit existing buildings. Part of the large expense of reusing gray water is when gray water is taken from sewage treatment plant and has to be shipped long distances through purple pipe, the infrastructure is quite expensive. So the idea was to do this locally within a building. But first, to reduce the water use through high efficiency fixtures, and again, to address the two scales of gray water. We have basically the process here to compare the performance of the buildings pre and post retrofit. And as we describe both of the demonstration sites, we'll tell you how they differed in the pre and post assessment. Next slide, please. So the next set of 3 slides, this is the detailed listing of the performance objectives and results, and we're going to go into this in more detail later in the presentation. So we're just going to ask you to go through this quickly, the next 3 slides. Okay, so on then to slide 9. So slide 9, describing our technical approach. Our goal was to reduce overall building water use, building potable water use, that is, by 30% within the building based on the technologies that we are incorporating in 2 different water regions. And right here we see the photos of the 2 regions. We have the very arid, dry southwest region, and then we have the not so arid and dry Midwest region. And so there are different drivers for water conservation in both of these regions. And our approach was what we call the cascading approach, and that is using the appropriate source of water for the need, for the end use. Whereas potable water is needed for uses that make contact with humans, and non-potable water is perfectly appropriate for uses such as flushing toilets or flushing urinals. And we also included some control technologies within our demonstrations. Next slide, please. So we should be on slide 11 here for test design. So in the case of our CERL facility, we performed before retrofit water metering. And we will discuss in detail on the MCRD site how we were documenting a system there. So it was a brand new building that was built, and we didn't monitor before. We just monitored the existing conditions. Then we conducted the retrofit, and then we did post-retrofit monitoring, and then analysis of the data and recommendations. Next slide, please. So we're on to demonstration site 1. The demonstration site 1 was our local facility that we work in here at CERL. And we isolated ourselves. You can see from the aerial photograph there's a number of buildings there. We isolated this project to the main complex of 3 large buildings to the left of the photo, building 1, 2, and 3. And this is where most of the offices are contained and also where some lab facilities are contained. So we addressed the small-scale, under-sink gray water reuse in these facilities, and we also incorporated the plumbing retrofits here. And we included monitoring both site-wide, we monitored the building level water use, and then we did some auditing of the fixtures so we could monitor fixture level use. And we as well monitored the bathroom that contained the under-sink gray water reuse system. Okay, next slide, please. So our first technology that was implemented at the CERL site were simply water-efficient fixtures. And we did some auditing. We did the kind of auditing you've seen with the plastic bags and the stopwatch and timing and looking at flows and identifying leaks and conditions. We also identified some other problems like sensor operation on the toilets. And we were not replacing toilets as part of this project, but we did get involved in adjusting the sensors and learning how those worked. So next slide, we should be on slide 14, which is the distributed reuse. I'm going to turn it over to Dr. Page.
So we were really excited to try and incorporate a pretty new concept and technology into this demonstration study. That put us on the bleeding edge a little bit, and we'll get into the details as to how this went. But the general concept that we approached the project with was to take a system, at least a concept, or framework that's been marketed and deployed in some cases for residential settings where water is taken, treated directly from the sinks or the sink drains and then used locally in the same bathroom to flush. So this is kind of an alternative to a building scale centralized system. It's a very small scale, but the idea was that if we took this approach, we might be able to come up with something that might have lower retrofit costs and that you don't have to get the whole building plumbing to implement the system, and it's something that can be rolled out one bathroom at a time, starting with some of your heavier bathrooms or heavier water use intensity bathrooms. And another idea with this was that we could take these technologies and hopefully, kind of target them to high visibility and high water use bathroom areas. One final aspect is that with water reuse, particularly in office settings, where your predominant uses are toilet flushing, hand washing, this seems like a system that might be implementable in a lot of building types that are DoD representative in terms of just general office space. Next slide. So this kind of summarizes some of the work and preliminary work that's fed into this demonstration project. So at the outset of the project, a little bit before, we were able to work with Sloan Valve Company to come up with some prototypes. We actually tested 2 different prototypes, one built by them, one built by us here. Did head-to-head testing at the laboratory scale under a CRADA with them, so that was some leverage funding that we used for this program. And then based on that, we down-selected and came up with a final design for the under-sink system to be demonstrated in this study. So the general technologies, we go to the next slide. We had an upflow biological activated carbon system, and our work in this space actually, we'll talk about later in tech transfer, led to some proprietary developments here for gray water treatment specifically, and we were able to get this system designed to minimize the overall complexity but still meet the water quality requirements for commercial settings. So one of the big jumps from going to a residential model to a commercial model is we suddenly had to worry about, well, what are the regulatory requirements in a commercial or publicly used bathroom for gray water reuse, which were quite a bit different, and the design required basically a lot more treatment, which was certainly a challenge to automate all this and implement it. So in this program, we planned 2 phases of testing, one being an offline test within the bathroom with no water reuse demonstrated, but still treating the sink water that was coming into the system. We originally planned that for a 3-month time period and ended up extending it to 5 months. Throughout the tests, we observed some needs for improvement and didn't feel comfortable integrating this fully with the sinks and toilets. So we just got to the point of integrating with the sinks only. But we collected a lot of really good data that basically will help shape a path forward for this system.
Yeah, and what you see on the bottom right in the slide, Martin deserves a major pat on the back. There is no code here in Illinois for gray water reuse, but they're interested in developing one. On the bottom right is when the Department of Health came, and they're collecting data from a lot of different demonstrations and using that to inform the development of the state code.
All right, we'll go to the next slide and back to Elizabeth here.
Sure. So our second demonstration site, I mentioned earlier we had some contracting obstacles. Initially, we had planned to install a building-scale gray water reuse system, and that was going to be at Fort Irwin. And when the contracting difficulties made that very challenging, if not impossible, we identified a site that already had building-scale gray water reuse systems in them, and we were allowed and able to document those instead to fulfill this part of the project. So what you see here are some of the interiors of the facility at MCRD San Diego, and this is the Walker Hall complex. This was constructed, an MCA construction project, opened in 2012, and it was designed for LEED Gold, and it indeed, one of the buildings met Gold and 2 of the buildings met the Platinum standard. So it also had some solar panels, but had the gray water reuse as an extra add-on that the users wanted. We had 3 buildings in the complex. The Smart Clinic, which has rehab for soldiers that get injured during, or Marines that is, that get injured during basic training, and then the medical barracks is where they stay while injured, and then a non-medical barracks. And we can see they have the gang latrines, which lend themselves to a centralized gray water reuse system within a building. You want to talk about this one?
Sure. So on the next slide for System 2 shows a little bit closer up on some of these gray water systems that were manufactured by Wahaso and installed. They implemented a fairly simple filtration system. Basically, the filters were designed in excess to provide continuous treatment. The treatment system itself, we felt by the end of the study, was probably not fully optimal, but it seemed to be providing good, acceptable quality of water in the case as it was being used on the site. They had 2 below-ground storage tanks, one for the influent gray water, which was collected from showers and sinks, or I should say showers or sinks. And then they had onboard metering capabilities. We did some extra metering as well with external meters. And so these systems were installed, again, new with the building. So this is a fairly optimal case in terms of looking at costs and everything, because these were put in with the building itself. And so this was a really good system to study for this program. So the next slide. I'll just reemphasize. So in this case, this is taking water from showers and or sinks, gray water, and then reusing that in the building just for toilet flushing only.
And so for the data collection out at MCRD, or actually I guess more generally, was measuring the water efficient plumbing, looking at the gray water collection and treatment systems for both of the systems, and also the monitoring and control. And so we had a series, I think we're going to go to the next slide, shows a little bit more the type of equipment we were using to collect data for this project. So on the top right, this is the display panel for the system out at MCRD. What we discovered was the users of the system were going out monthly and they were collecting meter data because this was not logging. So we devised a system where we installed data loggers. We kind of jumped the panel and collected data, continuous data, for what was available through that panel itself. And then we also, you can see the building water meter, that was the only water meter. Water metering is a real shortcoming in trying to validate this type of project, because we're fortunate if there is a meter on the building, because these were new buildings, they did have the meters. And next to that, in the blue encased box, what you see is that's a water meter flow recorder. And so we were collecting, we started out at 5-second interval data of water that was flowing across the meter, and that lets us get a little more detailed in our analysis rather than have one reading a month that's being collected manually. And then when you see the gentleman standing by the electrical panel, we installed voltage meters, and that was in order to see the electrical demand of the gray water system itself. And then the next photo on the far left, this is one of the meters that was feeding into the panel, and I believe that was produced gray water. But we wanted to collect that data over time. We didn't just want it once a month when the local staff was able to collect it. So these are some of the methods we use to collect data. So now on to the performance objectives, and we have a series of slides for each one of these objectives. We'll start out with the potable water usage. And okay, these are the results from at CERL. First, the graph on the top right is the pre-retrofit data, and it's color-coded according to these 3 buildings in the complex that we retrofit and we're monitoring. We can see some peaks in there. We learned a lot about our own buildings. Even though they've been audited before, we learned even more by collecting data and looking at it. So what we see in building, one of the buildings has a hydraulic pump. So you see the spikes of the hydraulic pump. And another building had a scanning electron microscope. And what we thought was kind of interesting here, and is pointed out in the text as well, is we discovered through the data that the scanning electronic microscope, which has got once through cooling in it, was running continuously. It wasn't being turned off because the cooling has to run for 15 minutes after a user's finished using it. So we identified that as a side benefit of metering for the purpose of our project. So the next one shows a couple things. The box calls out once we discovered this water was running all the time and we turned it off, that the water use immediately dropped. And then on the kind of the left of the graph, you see a little star. That's where our plumbing retrofits took place. So you can see how the water use dropped a little bit after that, and then the following year, the green line that shows 2016. And so I would like us to be able to claim credit for all this, but I don't think we really can. I have some charts on this, but the way we determined our water efficiency savings was from the audit method. The meters we installed, this is sort of the nature we found from a lot of the metering work we've been doing, is buildings that don't use a lot of water. We're primarily toilets, primarily sinks and showers here where we have locker rooms, but we have very large pipes, 3- and 4-inch pipes supplying essentially a building with a couple of bathrooms, and the meters are just not that fine resolution. So we believe that we were missing a bit of the water consumption of the building through that meter because of the size of the pipe. And some of the recommendations that came through, well, reduce the pipe size and put a smaller meter in, but we weren't really sure that that would be accurate if we wouldn't be creating an orifice there by dropping the size. But anyway, I just wanted to make the point of there was significant reduction. We don't believe it was all due to the plumbing fixtures, and we did use a model to validate the plumbing fixture reduction. And this is what our data look like for the CERL retrofit of the water fixtures. Here we have just the bathrooms and the locker room in one of the 3 buildings that we audited. And we have the pre and the post audit data showing the different flow rates. And this is where our figure that's also contained in the technical report came in of a 7% reduction. Now 7% is water use throughout the building. And part of the reason that that is so low is because we do have lab uses for water. We have a paint lab and chem and bio labs in our buildings as well. So we happen to be kind of unique as largely admin buildings, is that we have other major water uses here. But the fixtures themselves, you can see, reduce the flow quite significantly.
So one other technology we were interested in looking at in the context of locker rooms, but also we've been picking up chatter from people that have been working in the field that there's a need out there for a more efficient faucet type that can also clean razors. So I guess what happens in the field is that a lot of personnel will take aerators off of the faucet to increase the velocity of water or do various things, but basically it results in a really inefficient approach for just to clean their razors. So we worked with a company really in a very small capacity, but through this project to identify an alternative approach that could be useful in locker room settings, but also could be used in shade stands on the field or, say, in the containerized shower systems in the field as well. And we actually have training areas where we've seen a lot of this, like out at Fort Leonard Wood, where basically the sinks have been dismantled a little bit and the flow coming out is 2 to 3 gallons per minute, which not only is a waste of water, but it also takes away from the water pressure in the showers, et cetera. So we were looking at this system that has sort of a mechanical auto shut-off mechanism, so it doesn't require batteries. When we were doing market research on this, we were plumbers and other folks have just said that battery maintenance on the IR systems can be a bit of a pain. or if you've got something like a solar-powered valve, that it can be, those are pretty pricey. These were basically, could be swapped with the aerator on the faucet itself, and basically put in the commercial ones without the extra nozzle for a high velocity blast for shaving. So those are on the market for maybe $7 to $8 each. And then we had the company build us some custom prototypes, which we did some further work on to improve their functionality and at least get enough data to do some testing. So we think there's promise here. We didn't install it in a building, but we did some testing out on our experimental forward operating base here at CERL in Champaign. And then with the end goal of this moving out to Cibatec after we do some more testing. Next slide.
So as I mentioned earlier, at MCRD, because it wasn't a pre- and post-retrofit situation, we were documenting the potable water use. And this graph shows the potable water demand based on the readings from the meter, the monthly meter readings for the entire building. And we can see the two barracks buildings are a little bit higher and the clinic is fairly low. There is the last bullet there, what is found out by the end of this project, there was only one operational gray water system. We'll talk a little bit more about the reliability later, but by the time we were brought into the project of documenting their systems, the first system had already failed, and then through the period of our test, our demonstration, the second system failed, and so there was only one left that was operational. So the reason we documented the potable water for the other two buildings as well is to look at the theoretical possibility, if these gray water systems were operational, what the cost benefit and the payback would be. Because clearly the medical clinic uses the least amount of water. It's some therapeutic uses, there's soaking tubs and saunas and a therapeutic pool and a couple bathrooms, but the barracks themselves have the very large shower rooms and toilets and urinals. And in addition to collecting the monthly water use data and using the flow recorders, we also had collected population data from the barracks, and we can see that the water use pretty much correlates with the population. Population fluctuates a bit in the medical barracks depending on how many people are sick at a time, but the clinic is a pretty low population and it stayed pretty steady. So for the CERL, now we're on the gray water data. For the CERL retrofit, it took place in the Building 3 men's bathroom. And something we were interested in is how much, we wanted to look at a per capita basis of water use, both in terms of how much water would be generated from hand washing and how much water would be required from toilets. And so we had a couple different counters on the doors. And this is as good a time as any to talk about education of the building occupants, because it might be a little daunting to open the bathroom door and to see this electronic light flashing at you. We had signs posted outside and inside the door of the bathroom about the people counters, explaining what it was for, in addition to signs inside talking about the gray water system, even before it went in, informing the occupants of that building that this was coming, and if they had any questions, who they could contact about that. But we looked at a number of ways of counting people on installations, and this is a really important topic because we've dealt with this in other locations as well. It's very difficult to get real numbers, and if you're looking at a military installation, you have other factors to deal with. People that are visiting for training, retirees that are visiting the installation because they want to go to the PX, family members, do they live on post or off post? So counting people is no minor detail, and a lot of water use, even though we measure it a lot in gallons per square feet, it's really people that use water, so it's really important we figure out good and accurate ways to count people.
So we did have some numbers here as well in terms of what our kind of design objectives would be for a bathroom with water reuse capability. And this was in the case of a men's bathroom. Pre-retrofit, we were measuring about 284 gallons per day based on data collected and as well as model projections. and then we had a model post-retrofit that considered both if you replace the flush urinals that were in the bathroom with some lower flush urinals and updated the toilets, and then, of course, use the gray water from the sink to supplement your flushing demand. So the idea was that we wanted to get down to your only water demand, in theory, being for hand washing. What we found throughout the study is that the amount of water generated from hand washing activities, even with efficient toilets, might not be enough to cover your toilet flushing demand. So there's still going to be a little bit of makeup water there. But really, yeah, we could push towards that capability with a little bit more improvement of these types of systems. Sure. So we did collect water for the gray water system and collected data both from our meters installed out there, as well as some of the onboard metering feeding into the control panel. As Elizabeth mentioned, we didn't have baseline data for this site. The systems were all installed in fairly sustainable design buildings. But with water reuse, one of the nice things is you can look at, well, how much water you're reusing, and that gives you a sense of how much you're offsetting your potable demand. So that was kind of the basis we used for analyzing the data. As Elizabeth mentioned before, there were some issues with meters not fully capturing all the, at least building level meters not fully capturing all of the instantaneous water demand at this site as well. So we had to use the modeling and look at the data very carefully, and also install some of our own meters to kind of validate some of the data there. So now we'll transition to results for gray water quality. And I'll start going way back to when we were working on the CRADO work with the systems developed in coordination with Sloan Valve Company, where we did pre-testing and pre-validation of these systems under controlled conditions. There's a model we used for pre-validation of gray water systems from the industry that came about real early into this project. I think it was the final version was adopted in 2012, and that's the NSF 350, which is still referenced and used in a lot of guidance documents. But basically, the targets for that are get your biochemical oxygen demand, or BOD, down less than 10 mg per liter, and get your turbidity down low, make sure there's no bacteria in the water, and maintain some chlorine residual. So these are, when I discussed before, these are standards that apply to commercial or public type settings that weren't part of the equation for the residential systems, which were more really just based on having some chlorine in the effluent and not jamming up the valves in your toilet too badly. So the amount of design we had to put in was quite a bit higher than what was used in the residential model. So the pre-validation we did, this is data from a 2-month test, and the system seemed to be performing quite well. We did some intermittent loading, but it was relatively continuous compared to what you might see in an actual bathroom where your sinks are firing on and off. For the demonstration, the phase 1 demonstration, again, this is with the system installed in the bathroom but not hooked up to the toilets to flush those. We were still sending everything to waste at this point, just to collect data under realistic conditions. We were able to keep the system basically running autonomously for about 5 months. We sampled it very frequently. Andy Herr here helped with a lot of the water quality analysis and sampling, and did a lot of work to really characterize the long-term performance of these systems. So overall, the automation of the system was pretty good, and that's an absolute requirement for this type of setting where you're not going to have an operator that wants to troubleshoot anything. We did have some design issues that we're still working on here for the next generation of the system. And again, we tested this for 5 months, but then pulled it out of the bathroom afterwards. But we did have some issues with some of the internal controls, some of the pump level and demand pump pressure switches were keeping our pumps on longer than planned, which was costing us in energy. And then chlorine contact and getting the chlorine dose right over that extended period of time under that variable load was also a challenge. And one challenge that we've seen with these types of systems, both this one and the gray water system at the building scale, is that you've got to have a residual chlorine in your effluent and in the form of free chlorine. One thing we've seen is that in some of your waste coming into these systems, you can start to get some chlorine-demanding compounds like ammonia that react with the chlorine and can form other types of chlorine that are non-free chlorine, and those can present design challenges. I think that's probably information that we've learned out of this project from both this and the other systems that I think could be useful to feed back to the committees that work on things like the NSF 350, and that's basically having an awareness of things like ammonia in the water. So overall, the system works fairly well with regard to water quality. See comparisons of influent and effluent values. For the most part, we did see some minor spikes here and there, sometimes during operational downtimes for the building, like winter holidays. We particularly saw some issues with our biofilter performance, but overall, it was working well. So, good question. Somebody asked, where did the ammonia come from? So on our site here, there's actually combined chlorine coming into the building. So there's some ammonia residual in the hand washing water, and there's some chlorine that typically reacts with dirt. But that's one potential source. And then in the bathroom, in the shower system, that I'll get into in subsequent slides, ammonia can come in from just washing and proteins coming off people, but also urination in the showers is always an issue. We see that a lot in the field, more so than here, where in these systems, at least the shower systems we looked at, the ammonia was probably less due to urination, but because there were basically toilets in the same bathrooms. But in the field, we see, because the bathrooms and the showers are split into separate containers, we see a lot more urination. And so, sorry, yeah. I'm happy to answer that question anytime. So, good question. Okay, so this is some of our representative data collected from the influent tank and the effluent tank, and then we also did some sampling out of the toilets themselves to look at the point of use to see if the water quality changed during distribution within the building. But just comparing the influents and effluents, the system appeared to be meeting requirements for water use for toilet flushing in the field. We did see some issues again with the chlorine residuals. The chlorine residuals, even in the sinks in the buildings, were sometimes difficult to measure. Because the bacterial counts all looked good in the effluent samples, it seemed like the chlorine was doing what it's supposed to, but maintaining the residual wasn't always helpful. And again, the ammonia issue could be contributing to that through the breakpoint chemistry process. Go to the next slide here.
So our next performance objective is energy savings. And for the CERL site, all of our hot water is heated with natural gas. So we used a calculator, the Department of Energy FEMP, both a cost and an energy calculator, and calculated the amount of energy saved. And this one's showing fauceting. The next slide is going to show shower heads, and we just calculated based on one item. And we came up with a total amount of therms saved across the 3 building complex here of 260 therms per year. So not insignificant savings. And let's see, we're supposed to give this as a percentage of our water use, or of our energy use here. About 1% of our site's natural gas use would be saved by these water fixture retrofits here at CERL.
We installed some power meters on the site, on the control panels for the gray water reuse systems at both scales. This is data that was collected just showing energy consumption over time, pretty steady energy consumption. When we run the calculations on this, the watt hours per gallon comes out to be quite high. That's higher than what you'd use for heating your water, depending how cold your water was coming into your building. We're looking at these numbers in a little bit more detail to see what might be driving that energy cost so high. Just as a reference point, so when we design systems, say, for field operations where fuel is very important, we target energy consumption less than 20 watt hours per gallon. So the values we were observing are a little bit high, especially for a relatively simple treatment process.
Okay, the next performance objective is greenhouse gas. And again, using the energy that's saved by the fixture modifications, we just calculated for carbon. And that's a total for one fixture. So the total for the site here at CERL would be over 15,000 pounds of carbon avoided. And that is only due to the natural gas. So that won't be quite 1% because we also use electricity here on site. And so our next performance objective was system integration. And the only issue that we identified at all related to system integration had to do with the Building 3 under sink gray water reuse system. And Martin mentioned that if we reduce the flow in the faucets, we produce less gray water that can be treated and can be used to flush toilets. So in fact, in the Building 3 men's restroom, we did not retrofit the faucet aerators because we needed that water to supply the gray water treatment system. But that was the only issue we observed in this objective. The next objective is the life cycle cost. And starting with the fixtures, particularly when they are saving hot water, tend to be very cost effective and pay for themselves very quickly. And so, let's see. What I did here is three values for CERL. We typically do include the sewage cost in with the water cost when we're looking for life cycle cost savings for plumbing fixture retrofits. But we also include, if it's an appliance using hot water, then we include the hot water heating as well. So we came up with quite a quick payback in this case when we looked at water and energy costs. We do happen to have quite high water costs in this area, but the energy really made this technology pay for itself very quickly. We also identified, we also identified additional retrofits that could take place, and that's shown up here with the toilets. We had some toilets that used an awful lot of water. We had some 5 gallon per flush, but it's cold water. So the payback period is really not as quick as it is for the hot water consuming appliances, although we do recommend that the institution pursue those.
For the under-sink gray water system that we tested on site at CERL in Champaign, again, this is a system that optimally recovers 45 gallons per day if it's supplied with 50 gallons per day of water, and that's going to be dependent on how many users are in the bathroom. But when we did the life cycle cost assessment and used assuming 300 use days of the bathroom over a year, and using some of the costs for assembly of the system, which included labor projections for labor for that, as well as installation costs. Obviously, we didn't go all the way to hooking these up to the toilets with the installation. There were some additional requirements when we did the offline test for hooking into some sump pumps, et cetera. So we were able to estimate some of the installation costs, and they're really quite high relative to the savings over time for water reuse for toilet flushing. Again, we don't have that energy recovery aspect there. there were moderate consumable costs, pretty low maintenance costs. The system was fairly well automated, but you can see certainly if you want to get under a 10-year payback, which is probably about the lifetime of the system, then you're looking at needing your water cost to be $12.50 per gallon, somewhere in that neighborhood based on this model. If your capital cost of the system, and this is something we're working on now, can come down by changing around some of the components in the system design, that could be another way to get capital costs down. But during this demonstration, the system did not pay back in under 10 years. So we were going to have Andy talk about this, but he was just at the dentist, so I'll cover it. So with the water reuse system in Building 573, which is what we got most of our data off, that was a system that was up and running throughout the demonstration, demonstration period continuously. Even looking at pretty high water recovery levels, you can see that the payback is still going to be quite a long period, on the order of 40 years in this case, where we're just covering toilet flushing as the reuse application. One interesting kind of observation from this data is that in that top graph, as you increase the amount of water reused, if you can keep your capital costs similar, then you can improve your payback period quite a bit. So that was one of the key parts of the sensitivity analysis, is how much you can recover. And that really gets at what regulations allow us to do. Certainly in the field, we're designing and implementing systems that allow reuse in showers. I think that's a good direction for buildings to go eventually, to get these systems to be more cost effective. Another key parameter from the sensitivity analysis done by Andy was that the water cost, as that increases, if we shift that either 15% higher or 15% lower, that has a pretty substantial impact on your payback period. Things like energy, even though the energy efficiency on these systems was not optimal in my opinion, it was a relatively low contributor to the payback period. Capital cost, of course, is a key component as well. But some things with capital costs, like installation and retrofit, you're really not going to be able to do too much with that, even with better design.
So the next performance objective is reliability. We had no problems with the conservation technologies demonstrated at CERL. We didn't have any unplanned downtime for the undersink gray water system, but there were problems with the 3 building scale gray water systems at MCRD. And we have quite a number of findings that we're going to talk about in the end, and I think we'll cover all those problems that we found at MCRD. Okay, so up to system maintenance. We found no problem. We actually found no required maintenance with our fixture retrofits. This is a good time to point out, however, we have problems with toilets, and we did not retrofit toilets. They weren't included as part of the project. We did not replace toilets. Toilets have a required maintenance. It's recommended when they have auto flushers that those are adjusted every 2 years, and I rarely, if ever, hear of that happening on military installations, and so they typically are not functioning right. So that is something that should be known, even though it wasn't a problem for this retrofit.
So for the gray water systems, particularly at MCRD in San Diego, they tended to be a little bit high maintenance for the level of technical skill and capability of the staff there. So they had an HVAC technician that was monitoring the systems and adding chemicals, but when things went down, they didn't really have any capability to diagnose what was going on or make the corrections without a lot of time invested. So the design maintenance interval of 15 minutes per week was not really representative because they had periodic long maintenance times for when the system went down.
Locally here at CERL, we didn't have any complaints. In fact, part of our study was doing a user satisfaction or a user knowledge survey at the beginning of it, and the details of that are included in the tech report, and they're really interesting. People here, it's a research organization, so they were interested in the concept of gray water. Some of them are interested in it personally. So we found a lot of cooperation, and we did not get any complaints about the plumbing retrofit. I don't believe we got any complaints either about the retrofit in the Building 3 men's bathroom. Again, some questions about what was going on, but the system was never truly connected up to flush the toilet, so we didn't have that opportunity. At the MCRD, the people within the public works were dissatisfied with the gray water systems, but they were still enthusiastic about the technology. They wanted that technology there. They wanted to be on the leading edge of innovation. They just were dissatisfied by how the systems they owned were performing. So we have, I think, 3 or 4 pages worth of these. Some of these issues we've mentioned already. I'm just going to go down the list. The low flow issue with not capturing the data through the meters. We also had a problem. Our building automation system could not read the data from the meters as well for the same reason. So that's something that should be addressed. There's a compatibility requirement between a toilet bowl and a flushometer. You can't just take a new flushometer and put it on an old toilet bowl and achieve the design efficiency standards. So that's why we didn't try to do that on our own, and the bowls are the things that are expensive. The flush valve maintenance I mentioned, operation and maintenance folks, they have to know to stock the efficient replacement parts. The law requires water sense toilets. It does not require water sense efficient retrofit flush valves. And then with the topic of waterless urinals, originally we were going to include installation of that, but we found there were some requirements for installation that made that cost prohibitive for us to do the retrofit, and that's listed here. The monitoring, the adequate instrumentation for purchase systems, that refers to the Wahaso system in San Diego. It was very difficult, if not impossible, for us to really understand what that system was doing, because even the installed instrumentation wasn't adequate for us to be able to tell how much gray water is produced, how much makeup water is produced, and are they purging this tank every night? And so we really were, in some respects, doing our best estimating on how it was operating. For gray water application, we alluded to some of the code compliance, and I think we have some more details on subsequent slides on this. And Martin talked about the cost effectiveness of the gray water. The barracks buildings quite likely could have paid back in a reasonable amount of time, but that clinic that was the only system that was operational clearly was not paying back in any less than 40 or 50 years. And the idea that the building population has to be educated about how the systems are used. I'll talk about opportunities.
Sure. Some of the opportunities we've noted during this and other studies that it's rolling out some of these technologies, specifically the gray water reuse system, might make a lot more sense in some of the training areas at installation, where sometimes water is being trucked out in or out at very high cost to the training site. And then, do you want to talk about metering?
Sure. We've talked a lot about the metering already, but we've run into everything from 20-year-old meters in buildings to brand new meters that either aren't operational or aren't connected to building automation systems or are not being read at all. And so we have a gap in the knowledge there. We need to improve the metering capabilities. Part of what we're doing now in another project is we're benchmarking water use in different buildings, and we're going out and trying to find different metrics. Rather than water per square foot, we're looking at waters per meal served, water per acre of land irrigated, water per patient served in a health clinic. We think it's really important that we understand water use down to that level. I know we're a little over time, but I'd really like to go through these next slides and at least mention the bullets and see if we have any questions on these. In plumbing, there are regulations and some are contradictory. A lot of people on installations do not even understand what they're supposed to adhere to now because there are so many different compliance documents out there. Also, it's important to understand you can get too efficient. There are very ultra-efficient toilets that are not really recommended for large buildings, like large admin buildings with long horizontal runs of piping. So the 0.8 gallon per flush toilet's not a good idea for us to adopt in the Army. I mentioned about the retrofit versus replacement. O&M of waterless urinals, that used to be the standard in the Army, and it's no longer because of some of these obstacles there. The automated controls. WaterSense recommends that the sensors, the auto flush sensors, be adjusted every 2 years on toilets. I've never heard of an installation that's doing that. We found that ours were out of whack, and we adjusted them, and they worked a little bit better.
There are certainly approval processes, again, bleeding edge, doing this type of work at the building scale. A lot of times you're not going to have the staffing power to get through the approval process, particularly in states where there may not even be code yet. So that's, I think, a challenge to working on these problems at small scale.
Okay, on the next slide, this is all on the gray water.
So with the MCRD systems, they could have benefited from, say, the NSF 350 guidance that came out probably not too long after those were installed, and doing pre-validation testing on those systems to make sure basically they run autonomously without downtime. Because as stated, getting those systems, troubleshooting those systems was beyond the capability of staff. There's probably some contracting strategies that could be used too to make sure that sites get the support they need long term for maintaining those systems and keeping them up to avoid those downtimes and the associated frustration with that. For the smaller scale systems, I think some technical improvements still need to be made to bring down capital costs, and I'll leave it with that.
And we talked a little bit under regulations on this next slide. We talked a little bit about most states don't have a water reuse regulation. There is a water reuse code 22 in California that governs gray water reuse. But NAVFAC, who was responsible for this MCA project, was unable to find a government entity that would help them go through that code compliance process, not the county or the city, and so they were on their own. And that could have been the root of some of the problems with the gray water systems out there.
And as mentioned before, yeah, there's things that can be done on the contracting side to improve the support that an installation gets with installing some of these more bleeding edge systems. Another thing we're really interested on the economic side, and we've been talking to Mark Kodak at IE&E a lot about this, is with some of the new requirements, at least within the Army, for resiliency and energy and water security, thinking about some of the non-market valuation factors and how those might be brought into to analyzing the life cycle costs of these systems by incorporating some of the risk factors associated with a variety of potential things that cause downtime and loss of capabilities associated with that. So Andy Herr here is leading a project along with NOAA to look at non-market valuation factors specifically for water systems and how that could change how we look at these in terms of investment.
And that sort of leads into tech transfer, where we say potential first users in installations that are water stressed, but we see periodic droughts in many areas of our country that never saw drought before. We've had droughts in the southeast that's not usually considered drought prone. So perhaps the reliability of having a local water source, which is reused water, can be worth it. And one of the criteria we have in the Army, I know DOD does have a policy on water security, but I'm not familiar with it. But the Army has a policy right now that requires a 14-day backup supply for critical water needs. And so in that case, and with the non-market valuation techniques employed, perhaps gray water will be seen as a more economical possibility.
We're working actively to roll out lessons learned from this project into our work to support expeditionary or contingency basing type applications. And again, the market in training areas as well at installations. I think that's prime for installing some of these systems and getting them fielded, getting the culture of water sustainability infused into some of our military training. I think that could pay a lot of dividends in terms of speeding these systems up and doing so in a cost-effective manner. So that can impact both the installation community and also expeditionary operations.
So a number of publications throughout the study. We took a look at the UFC. Originally we said we were going to recommend changes to the UFC, but the UFC on plumbing references the UFC on high performance and sustainable buildings, which happens to be revised October 2017, and that has the correct criteria, at least for water conservation, and it does encourage water reuse where cost effective.
We did have a patent that's been filed for the self-cleaning biofiltration system. Again, that was developed, and we're still studying that for a wide range of applications to support military-specific requirements relating to water treatment, and including incorporation of that as a key component in one of our field water recycling systems that we're going to be transferring to PDM, petroleum and water systems. We are thinking a little bit about the social media content aspects. We have some links that could be shared to support that, but we didn't get too far down that path. Certainly, social marketing of some of these capabilities and that things like water use, that those can be done in a safe manner, and that those things are happening throughout the country. I think that's always helpful.
So that's conclusion of our main slide deck. Do we have any more questions? Okay, Sarah, I turn it back. Thanks.